Hello everyone, welcome back to the channel. So today we are doing Leetcode 2563, count the number of pair pairs. Let's have a look at what the question statement says. Given a zero indexed integer array nums of size n and two integers lower and upper, return the number of fair pairs. So again, what is a fair pair? A pair I comma j is fair when these two conditions hold. I should be less than j and I and j both should obviously be valid indexes, and the sum of nums of I and nums of j should be in between and inclusive of lower and upper. Okay, so if you have two such indices I and j, and such that the sum of the value at those indices lies in between lower and upper inclusive, then that constitutes a fair pair. Okay, now let's have a look at the example test cases. Okay, 0 1 7 4 4 5, lower is 3, upper is 6, and then 1 7 9 2 5, you just have a single fair pair, and that is at index 2 comma 3, which means you can only make up 11 when you use 9 and 2. So let's have a look at the first test case over here. I have 0 1 7 4 4 5. Okay, now for this 0, let's say I am standing at this 0. So what is the least amount of number, what is the least amount of value that I need to put together with this 0 in order so that the final value becomes in between 3 and 6, right? So I at least I need to add 3, right? So that I have this range 3 to 6, so that if I add 3 to 0, then I will be standing over here. And then what's the maximum number that I can add to 6? That is 0 plus 6, so I will be standing over here. So these are basically the boundary values, right? So I can do anything like 4, and I can do 4 and 5 as well. Both of them are also going to be inside of the range, right? So what I'm going to do is, having this information in my mind, I'm going to iterate through the remaining array. I'm going to see if this is greater than 3 and less than 6. So if this belongs to 3 4 5 6, no it does not, so it does not constitute a good pair, right? Then I'm going to see it for 7. No. I'm going to see for 4. Yes, 4 does. So that means that I can pair this 0 with this 4. Perfect. I can also pair it with this 4. I can also pair it with this 5. So that means that this 0 is going to constitute, it's going to give me 3 different pairs. Okay, now then I am standing at this particular one. When I'm standing at this one, what do I add to this one so that the sum lies in the range 3 to 6? At minimum I need to add 2, at maximum I can add 5. Not less than 2, not greater than 5, isn't it? So with that in mind, I'm going to iterate through the rest of the array. Is this, I have this particular range in mind. Okay, 2 3 4 and 5. I can at maximum add 2, or and sorry, at minimum I can add 2, and at maximum I can add, no sorry, I can at maximum I can add 4. Right, at maximum I can add 4, because the sum cannot proceed above and beyond 6. So is 7 part of the game? No. This 4, yes. This 4, yes. This 5, again. I can have this 5 as well, right? Yeah, I can have this 5 as well. Sorry, I got a bit confused. Because 1 plus 5 is going to be 6, right? So I can pair this 1 up with this 4, and this 5. So again, this is going to give me 3 pairs as well. Now this 7, I don't even need to process this 7. Why? Because it is already beyond my limit, and I don't have negative numbers inside my array. So there's no chance that this 7 is going to become any smaller. So just don't process it at all. Now this 4, what I know about this 4 is that I can pair it with whom? I can pair it with 0, and I can pair it with this 1, isn't it? 4 plus 0 is 4, it lies in this range. 4 plus 1 is 5, it lies in this range. But then I already have counted the pair 0 comma 4, isn't it? So I need to avoid repetition. I need to avoid, if I have taken 0 comma 4, I do not need to take 4 comma 0 again. If I've taken 0 comma 5, I do not need to take 5 comma 0 again. So that means that for a certain index, I am not going to look behind it. I am only going to look beyond it. Okay, so for this 4, I'm going to see if there are any numbers which are in front of this 4 that I can take in order, so that the sum, lies inside this range. There is no such number. Similarly, there is no such number for this 4. There is no such number for this 5 as well. So overall, my answer becomes 3 plus 3, which is 6, which is the same answer which we get over here as well. Now, similarly, if we try to traverse over this particular, this is basically the second test case which Leetcode has provided to us. The lower boundary is 11, the upper boundary is also 11. Okay, so if I'm standing at this one, the lower number which I can uh, put together with this one, if 10, and the highest number is also 10, because the lower and these both are equal to each other, right? I don't have any 10, so I'll iterate through the array. I will observe at the end that I do not have any array, so this one does not actually add up anything to my answer. This 2, when I iterate through the array, I find this 9, isn't it? When I combine 2 plus 9, it gives me 11, and 11 is actually inside this range. So that means that this 2 constitutes 1 to my overall answer, right? Then I'm standing at 3, nothing happens. Standing at 7, nothing happens. Standing at 9, nothing happens. And that's the end of it. Now, do you notice something about this test case which maybe, sort of optimizes the way, optimizes our solution a bit? Do you notice something which is, a characteristic of this array, something which is different in this array as compared to the first test case? That is something which we are going to look at. But before that, let's build up our intuition a bit. For each number, for 0, I had to traverse this whole array. Then for 1, I had to traverse this whole part of the array. For this 7, I had to traverse this whole part of the array, isn't it? So what I'm doing is I'm basically like traversing O of n times. That means that the overall time complexity of my code is going to be O of n squared, isn't it? Because what I'm really doing is, for this particular item, I'm iterating almost over the whole array, isn't it? And for this item, I'm iterating almost over the whole array. So this is clearly something which is on the order of O of n square. Now, if we take a look at the constraints of our problem, this is 10 to the power 5. So if we are doing O of n square to 10 to the power 5, then that means 10 to the power 5 square. And this is way beyond our acceptable limit, which is 10 to the power 8, isn't it? So maybe we need to do something which is better than O of n square, maybe something on the level of n log n, or maybe something which is on the order of O of n. Now the question is, how do we do something which is better than O of n square? Take a moment at this point, pause the video and think about it. You see, the part which is causing redundancy is that for each number, I have to check the whole of the array, isn't it? For each of the number, I have to check the whole of the array. So can I do something on this array such that I do not have to iterate one by one? Can I do something like that? Think about it. Why don't we sort the array? So this was our original array, right? This was our original array. And if I sort it, it becomes 0, 1, 4, 4, 5, 7. Now you see, after having sorted the array, there is no point in doing linear search, right? If I had to do linear search, why would I sort the array in the first place? And what do we do when the array is sorted? We think in terms of binary search. So let's see if binary search fits our use case. Okay, now the minimum is 3, the minimum limit is 3, the maximum limit is 7. I need my I need such a sum. Basically, I need to combine something with this 0 such that the resulting thing falls between 3, 4, 5, 6, isn't it? So what I'm going to do, I'm not going to iteratively go on this array. I'm going to apply binary search on this part of the array. You're getting my point? So the first mid which will be calculated is going to be this 4. Then I'll have to decide whether I want to move on to the right side, whether I want to move on the left side. So basically, something which I was previously doing in O of n, now after having sorted the array, it's going to take O of log n. So previously we were doing n times O of n. Now we will be doing n times O of log n. So the overall complexity becomes n log n, which is completely acceptable, isn't it? Now the thing is, how am I going to apply binary search over here? That's the question, right? So for that, it's very important that you have a very good idea of how lower bound works. What does lower bound give you? Lower bound basically returns an iterator. Okay, it gives you the index of the first element which is greater than equal to what you are searching for. Okay, which in the index of the first element which is greater than equal to the element which you are searching for. So on the minimum side, at the minimum side, I'm searching for 3. So what I will do is I will apply lower bound, and I'll say to that lower bound that your search space is what? Your search space is from 1 to 5. Okay, I'm going to say that, and then what I'm searching for is 3. So what is this lower bound going to return me? This lower bound is going to return me the first element which is greater than equal to my target, which is actually equals to 2. So this lower bound gives me 2. Okay. Then similarly, I'm going to I'm going to ask I'm going to ask another such query, and I want to see that how many numbers can I take at the higher end. Okay, how many numbers am I going to take at the higher end? So if I apply lower bound on 1 comma 5, and if I give it 6, so it's going to return me the element, it's going to return me the index of the first element which is greater than equal to my target. So it's going to give me what? It's going to give me 7, isn't it? Now you see, if I do 5 minus 2, I get 3, and 3 is the exact contribution which this 0 is making. Are you getting my point? 3 is the exact contribution which this 0 is making. Now, this is not the correct approach. We are building our way towards the correct approach, right? Now, I'm going to do the same thing with this one. Now, for this one, I know that at minimum, I can, I can add 2 to it, and then at maximum, I can add 5 to it. So I'm going to say, I want to search over this search space, okay, from 2 to 5. And what am I searching for? I'm searching for 2. So inside of this uh, inside of this particular subarray, what index am I going to get? I'm going to get the index I'm going to get index 2, isn't it? Because that's the first element such that it's greater than my target, right? And then again, I'm going to say that 2 comma 5 is your search space, and the max, and 5 is actually what I'm searching for. So it returns me the index of the first element which is greater than equal to my target. So it's going to return me what? It's going to return me 4. Thing is, 4 minus 2 is actually equals to 2, but then if you remember from before, 1 was contributing 3 elements and not 2, isn't it? The only thing which is different is, for the maximum part, I do not take a lower bound, I actually take an upper bound. The difference between lower and upper bound is that lower bound gives you the index of the first element which is greater than equal to your target. Upper bound gives you the index of the first element which is strictly greater than your target. Okay, strictly greater than your target. So that's why upper bound of 2 comma 5, when your target is 5, it's going to give you, it's not going to give you 4, it's going to give you 5. Why? Because 7 is strictly greater than 5. And then when you do 5 minus 2, what are you going to get? You're going to get 3, and 3 plus 3 is basically your answer. So I hope the thought process is clear to you, and at this point we have basically, solved this particular problem for us. So I'm just going to go towards the code. I've sorted the array over here. I have taken a variable known as ans. I've initialized to 0, and basically what we are doing, as you can see over here, is I'm iterating one by one through the array, right? First I do the job for 0, then I do the job for 1, then I do the job for 4, so on and so forth. So I'm iterating through the array, and what am I basically assuming? I'm assuming that I'm currently at nums of I. So in the first iteration, I'm assuming that I'm currently at 0. Then I'm currently at 1. Then I'm currently at 4. And basically what I'm doing is, one thing is that we are calculating the lower bound, right? We are calculating the lower bound. We are saying that the start should be nums dot begin plus I plus 1. So it should be like one step towards. So for example, if I'm standing at 0, the start should be this, isn't it? If I'm standing at 1, the start should be this. That's why nums dot begin plus I plus 1. So I need to start from here. Okay, I hope this makes sense. Right. So what I've basically done over here is I've said that I'm calculating lower bound nums dot begin plus I plus 1. The ending is nums dot end obviously, and what I'm searching for is lower minus nums of I. Now, why am I searching for lower minus nums of I? Just think about it. You see, this was originally, this was the line of, this was the line which was told to us by the question statement, right? That nums of I plus nums of j should be in between lower and upper. What if I subtract nums of j from both lower and upper? So something like this. What if I do something like this? What I'm simply doing is that I have subtracted nums of j from both the sides, from lower and from upper. That is why basically, and you must have noticed, right? What we were calculating over here is minimum of 2. So what is that? That is nothing but 3 minus 1, 2. 5. That is nothing but 6 minus 1, isn't it? So that is exactly what we are doing. Okay, lower minus nums of I is basically my target. And why am I subtracting nums dot begin from this lower bound? Because that way, I said lower bound actually gives you the iterator. I do not want the iterator, I actually want the index. So if you subtract nums dot begin from the lower bound, it's going to return you the index rather than the iterator. Okay, similarly, I'm going to calculate the upper bound. I'm going to say the same search space, nums dot begin plus I plus 1 nums dot end, and the target which I'm looking for is upper minus nums of I, isn't it? In the end, I'm just going to add the difference between high and low. I'm going to convert it into long, and I'm going to add it to the answer. Why are we converting to long? Because of this, we need to return our overall answer in long. So if I submit this code, let's see if it passes all the test cases. And it very clearly does. So the time complexity very clearly over here is n log n, and we are not taking any extra space, so the space complexity is O of 1. So this was a very good example, a very good application of how binary search actually optimizes our brute force solution. Our brute force solution was very simple. The brute force solution was calculate all the fair pairs, O of n square solution, right? But then how binary search is able to optimize this and take our time complexity to O of n log n. So I hope you found the video helpful, and I'll inshallah see you in the next one. Take care.